Hello friends, welcome to our YouTube channel. A complex electrical network can easily be analyzed if we consider it as an interconnection of several smaller and simpler modules. This not only helps to solve the problem easily but also reduces chances of error. Designers, when design a complex network, they design simple two-port modules and then interconnect them. This leads to error-free design and makes things simpler. It is also easier to shield the smaller units to reduce the parasitic capacitances to ground. A variety of interconnections are feasible. Today we shall discuss series connection of two-port networks. Two-port networks can be interconnected in various ways. When we connect output port of one two-port network to the input port of another two-port network, we call it cascade connection. It is the simplest method and a very popular one. The overall transmission parameter matrix for cascade connected two-port networks is the matrix product of the transmission parameter matrices of each individual two-port networks connected in cascade. The overall inverse transmission parameter matrix for cascade connected two-port networks is the matrix product of the inverse transmission matrices of each individual two-port networks but in reverse order. When both the input ports and output ports are connected in series, we call it series connection or simply series connection. The overall Z parameter matrix of series connected two-port networks is the sum of Z parameter matrices of each individual two-port networks connected in series. When both the input ports and output ports are connected in parallel, we call it parallel connection or simply parallel connection. The overall Y parameter matrix of parallel connected two-port network is the sum of Y parameter matrices of each individual two-port network connected in parallel fashion. When input ports are connected in series, output ports are connected in parallel, we call it a series parallel connection. The overall hybrid parameter matrix of series parallel connected two-port networks is the sum of hybrid parameter matrices of each individual two-port network connected in series parallel fashion. When input ports are connected in parallel, output ports are connected in series, we call it a parallel series connection. The overall inverse hybrid parameter matrix of parallel series connected two-port networks is the sum of inverse hybrid parameter matrices of each individual two-port networks connected in parallel series fashion. Today we shall talk about series connection. Let us see how we can connect two two-port networks in series connection. We have a network A having open circuit impedance parameter matrix ZA. Its input and output port voltages are V1A and V2A respectively. We have a second two-port network B having open circuit impedance parameter matrix ZB. Its input and output port voltages are V1B and V2B respectively. Let us connect the input ports in series and also the output ports in series. Let the input and output port voltages of the combined network be V1 and V2. The input port and output port currents of the combined network are I1 and I2 respectively. Let us assign the input and output port currents for network A and network B. The input and output port currents of network A are I1A and I2A. The input and output port currents of network B are I1B and I2B. At the input port, we can observe I1 equals to I1A equals to I1B, as the input ports are connected in series. Applying Kirchhoff's voltage law at the input port, we can write V1 equals to V1A plus V1B. As the output ports are connected in series, we can write I2 equals to I2A equals to I2B. Applying Kirchhoff's voltage law, we get V2 equals to V2A plus V2B. Let us derive the overall Z parameter matrix for two series connected two-port networks. When we describe any two-port network using Z parameters, we express input and output port voltages V1 and V2 in terms of input and output port currents I1 and I2. For network A, we can write V1A equals to Z11A I1A plus Z12A I2A, and V2A equals to Z21A I1A plus Z22A I2A. For network B, we can write V1B equals to Z11B I1B plus Z12B I2B, and V2B equals to Z21B I1B plus Z22B I2B. For the combined network, we can write V1 equals to Z11I1 plus Z12I2 and V2 equals to Z21I1 plus Z22I2. As the input ports are connected in series, we can write, applying Kirchhoff's voltage law, V1 equals to V1A plus V1B. Using expressions of V1A and V1B, we get Z11A plus Z11B times I1 plus Z12A plus Z12B times I2. Because I1A equals to I1B equals to I1 for series connected input ports, and I2A equals to I2B equals to I2 for series connected output ports. Applying Kirchhoff's voltage law at the output port, we get V2 equals to V2A plus V2B. Applying expressions of V2A and V2B, we get Z21A plus Z21B times I1 plus Z22A plus Z22B times I2. Comparing the expressions of V1, we get Z11 equals to Z11A plus Z11B and Z12 equals to Z12A plus Z12B. Comparing the expressions of V2, we get Z21 equals to Z21A plus Z21B and Z22 equals to Z22A plus Z22B. Therefore, we can write matrix of Z equals to matrix of ZA plus matrix of ZB. Hence, we can conclude that the overall Z parameter matrix of series connected two-port networks is the sum of Z parameter matrix of each individual network connected in series connection. This result may be generalized for any number of two-port networks connected in series subject to the condition of interconnectibility being satisfied. Let us solve a numerical problem. We have to find out the Z parameters for the network shown. Here we can see network A and network B are connected in series connection. To find out the overall Z parameter matrix, we have to find out the Z parameter matrices for network A and network B separately. First, we shall find the Z parameter matrix for network A. Let the input and output port voltages be V1 and V2 and the loop currents I1, I2 and I3. Applying Kirchhoff's voltage law, from loop 1 we can write V1 equals to I1 minus I3. The second equation we obtain is V2 equals to I2 plus I3. From the middle loop we can write 0 equals to minus of I1 plus I2 plus 10 I3. Therefore, we can write I3 equals to 0.1 I1 minus 0.1 I2. Using this expression in equation number 1, we get V1 equals to 0.9 I1 plus 0.1 I2. From equation number 2, we get V2 equals to 0.1 I1 plus 0.9 I2. The linear equations we used to describe any two-port network using Z parameters were V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Comparing these two sets of equations, we get Z11 equals to 0.9 ohm, Z12 equals to Z21 equals to 0.1 ohm, Z22 equals to 0.9 ohm. Therefore, we can write matrix of ZA equals to matrix of 0.9, 0.1, 0.1, 0.9 ohm. Let us find out the Z parameter matrix for network B. Let's assign the input and output port voltages be V1 and V2 and the loop currents are I1 and I2. Applying Kirchhoff's voltage law, from loop 1 we can write V1 equals to 6I1 plus 3I2. From loop 2 we can write V2 equals to 3I1 plus 6I2. The linear equations we used to describe any two-port network using Z parameters were V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Comparing these two sets of equations, we can write Z11 equals to 6 ohm, Z12 equals to Z21 equals to 3 ohm, Z22 equals to 6 ohm. Therefore, we can write matrix of ZB equals to matrix of 6, 3, 3, 6. So, matrix of ZA equals to matrix of 0.9, 0.1, 0.1, 0.9. Matrix of ZB equals to matrix of 6, 3, 3, 6. We know that the overall Z parameter matrix of series connected two-port networks is the sum of Z parameter matrices of each individual two-port network connected in series. Therefore, we can write matrix of Z equals to matrix of ZA plus matrix of ZB. So, we can write matrix of 0.9, 0.1, 0.1, 0.9 plus matrix of 6, 3, 3, 6 equals to matrix of 6.9, 3.1, 3.1, 6.9 ohm. So, we have learned today that when both input ports and output ports are connected in series, we call it a series connection or simply series connection. We have derived the expression for the overall Z parameter matrix of the combined network. We have found that the overall Z parameter matrix of series connected two-port networks is the sum of Z parameter matrices of each individual two-port network connected in series fashion. We have solved a numerical problem to obtain the overall Z parameter matrix of two-port networks connected in series fashion. That's all I have for you today. I hope this lecture has been useful for you. If you have any questions or suggestions, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends.